We are solidly into the unit covering Gauss's law. We need to introduce the concept of electric flux, and this is a concept that will prove useful later in the course when we're covering magnetic flux as well. Here we're going to define flux. We use capital Greek letter phi with an E subscript to keep it separate from magnetic flux later in the course. And you'll find this information in chapter 22 of Young and Friedman text. The electric flux is defined as the dot product of the electric field vector at some location with a dA vector at that location. When we discuss flux, we're thinking about a surface, say the surface of your phone. If you were to walk out in the rain and you want to keep using your phone, you're not going to hold it horizontally where the raindrops are going to pass primarily through the screen of the phone. Your goal would be to expose the phone to as little rain as possible coming vertically downward. You would hold it like this and look at it face on. So here you are minimizing the flux of raindrops, if you want to think of it that way, through the surface of your phone. Here, electric field vectors are not flowing, they're not moving with time. We're discussing electrostatics still, so these vectors are just fixed in space, but you can still think about the tendency of those vectors to appear as though they are passing through any surface area. In order to compute the flux, you'll need to define an area vector, A. It has magnitude equal to the area of that surface, and it has a direction which is perpendicular or normal to the surface. The n hat is the unit vector, which is normal to that surface. It has, of course, a magnitude of 1. It does not carry physical dimensions. The area vector itself has units of area, meter squared. In practice, we first have to consider every small bit of area, dA, as we have done in previous problems, and then integrate it up to cover the entire area A. If the electric field is uniform along that surface, in other words, it is the same vector everywhere on the surface, the flux becomes easier to calculate. We'll see that later. Bear in mind this rule that the normal vector is going to point out of any curved or closed surface. So if there is a sort of identifiable concavity or convexity to your surface, you want to imagine the normal line to that surface or the normal plane to the surface, and then your normal vector will be perpendicular to that. If you have a flat surface, there's some ambiguity about which way to draw your area vector. Often we will just pick something convenient that will make the electric flux positive, but in that case the sign of your flux is completely dependent on how you define that area vector. So if you want to compute the electric flux through this surface A, we need to first get the differential or infinitesimal flux through each small patch of area, dA, and you get that by computing the dot product of the electric field and the dA vector. The dot product gives you E dA, the magnitudes of the two vectors, times cosine theta. The total flux through the area A here, or surface S, which has area A, will be a surface integral indicated by this subscript S of dE, the individual fluxes through each patch of area. Right? So we're adding up the infinitely many small fluxes through each patch dA, integrating up E dA cosine of theta. In practice, the electric flux can change a few different ways. Okay, you can change the angle between the electric field and the area. Okay. You could change the area, the size of the area itself, or you can change the electric field magnitude. These are things that may vary along the surface S if the electric field is not uniform. Okay, that angle and electric field magnitude may be different everywhere along the surface, but in general we'll for now consider things that are not changing in time. They are constant. What are the units of electric flux? You have, in general, let's say the simplest case, E dot A, if the vector electric field is uniform over your surface, then units of E dot dA are newtons per coulomb, that's our familiar unit for electric field, times meters squared. If you're stuck, say you forget the units of electric field on an exam, you could recover those quickly using the simplest equation you can think of that contains electric field. So you say, I know F equals QE and force is in newtons, charge is in coulombs, and I forget the units of E, so we solve for the units of E, and you find newtons per coulomb. Okay? So you have Newton meters squared per coulomb is the unit of flux. Let's run through a quick example that shows a calculation of flux. So we could imagine a cube sitting in a uniform field. The electric field is given by a constant A I hat plus another constant B J hat plus another constant C K hat. What is the total flux or net flux through the cube? Well, that cube has 6 sides or faces. We'll say length L. So we're going to have to individually compute the flux through each of 6 sides. So let's place the cube in a standard right-handed coordinate system. And for now, we'll just consider side 1, or the front of the cube, as we're facing it here, its dA vector, now of course each face has its own individual dA vector, but this one is coming out of the page at you, called it dA1, has magnitude dA1, it points in the plus k hat direction. We'll assume the cube is oriented along, it's parallel to the 3 usual axes, x, y, and z. And we'll add another rule here for closed surfaces, like this cube. Flux will be positive if the electric fields sort of facing out of the surface, and flux will be negative if the electric field vectors face in. Okay, that will become clear as we use the rule in various calculations throughout. Now we haven't sketched out the electric field here yet. Why? Because its direction is unknown. It's just left in terms of these constants. All we can say is that these E field vectors should everywhere be in the same direction and have the same magnitude. So we can put in some representation of that. So you can see now there will be negative flux along certain surfaces of the cube where the E fields appear to be entering the cube, and then there will be positive flux for other surfaces where the E field vectors appear to be leaving the cube. Okay. So flux through surface 1 looks like a surface integral over area 1, or surface 1, E dot dA1. We have the representation of that electric field stated in the problem, AI hat plus BJ hat plus CK hat, dotted now with the vector dA1 K hat. Well, here are 3 different dot products. Okay, you can distribute the dot product. So we have 3 terms here. There's A dA1 I hat dot K hat plus B dA1 J hat dot K hat and C dA1 K hat dot K hat. So you'll need to review your rules about dot products. Of course, I hat and K hat are perpendicular. So when you dot them together, you have a cosine 90 that gives you 0. The dot product of any 2 unit vectors that are orthogonal is 0. So the only term that survives here is this K hat dot K hat. Those are unit vectors pointing in the same direction. So you have a cosine 0, that gives you 1. Right, these here were because, say, I hat dot K hat equals the magnitude of each 1, 1 cosine 90, which was 0. Over here, K hat dot K hat is 1, 1 cosine 0. That should be familiar to you. So overall, for that surface, we bring the constant out. We have the area integral over dA1. What does it mean? It just means sum up all the bits of dA area along that face, and you will get the area of the face, not surprisingly. So with a side length of L, both ways, that area is L squared. Okay. Well, we won't do all 6 of them, but let's just quickly consider the back. The back face, which I'm calling 2. Your dA vector will be similar to this one, except it will point in the negative z direction. It's facing outward from your surface always, so dA2 magnitude vector is minus k hat. You can dot, 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 like go through the calculation we just went through. Your flux 2 will still come out with zeros on these 2 terms, but now you have a minus k hat sitting here, so this term will become negative c dA1. You'll integrate over the dA2s in this case to get L squared, and that flux will be minus CL squared, opposite the flux through surface 1. So we would repeat here, and I'll leave that as an exercise for you. Repeat for the top and bottom together. You might guess that the net flux there will be 0. You repeat for the right and left surfaces. Those fluxes will also add to 0. So we have a result that you should try to prove, that the net flux through the entire cube is 0.